Get going. Let me thank Gordon Walker for, well, Gordon talked to us back in January on a different topic entirely, but he's volunteered again, so I'm very grateful for him doing that. We will try to continue having these talks if we continue to get an audience. So Gordon Walker, emeritus professor in our department, is going to talk about buckyballs in space. So take it away, Gordon.
Thanks very much, Douglas. Yeah, 2 lectures in such a short time, but then I don't know how much time I've got left, so I thought I would just get a move on. Diffuse interstellar bands. This isn't working. Now, why did that not work? There we go. All right, it works now. The diffuse interstellar bands were noticed in spectra at the turn of the last century, but it wasn't until Mary Lea Heger was able to demonstrate that a couple of them were definitely interstellar and associated with interstellar dust, which was a very new concept at that time. It was a brilliant piece of work. And can I get rid of these things on the side here? Yes, no.
I don't see anything on the side.
I've done it. So there you see an example taken from this excellent historical paper by Ben McCall and Elizabeth Griffin. They've put in some modern spectra, but it shows 2 of these bands there, which she was able to show were interstellar. And oh, I keep hitting the wrong key here. There we go. So here's an example of a very broad diffuse interstellar band. It used to be called 4430. It's now 4428. I did my doctoral thesis on that way back in '62. And this shows a reddened and an unreddened star by interstellar material. Shows a couple of stellar lines. And this very broad, powerful absorption, which nobody's been able to identify, but that's true for so many of them. If you look particularly in the red-orange region of the spectrum, there are myriads of them every few angstrom. And here, a whole lot of identified diffuse bands in the spectrum of this canonical star 183143, compared with Rigel. They're very similar spectral types. And you see 6284, which is a very broad feature, which actually corresponds with one of the atmospheric oxygen bands, and a whole host of them. And indeed, as much as one takes spectra of higher and higher signal to noise, these bands just appear in large numbers. There are at least 600 now known, but people don't publish the extra ones they find, as far as I know. They appear to occur in families. That is, they move together in terms of intensity. They're all tend to be correlated with interstellar reddening. And these are the bands out here corresponding to C60 plus, which I'll get around to talking about. I also like to include the 2175 bump in the ultraviolet. This is a huge feature, which is well known, I don't have to talk about, but is generally attributed to carbon. So I restarted working on the diffuse interstellar bands after I retired, which is what, 23 years ago. And I started working with David Bohlender here at the Herzberg Institute, who is a superb analyst of spectra. He does a wonderful job. He's very self-effacing. And at the same time, I got into contact with John Maier, because John Maier was attempting to look at the spectra of candidate molecules in his lab in Basel. And this picture is taken in 2001 at Halipahaku, and we had just completed a very successful and exciting run on that occasion because we were trying to establish, or at least helped to look at the question of whether the diffuse interstellar bands were due to long carbon chain molecules or Fullerenes. And the first step was to look for the shortest of the carbon chains, which was C3. And lo and behold, we did find that. And what you see here are the three spectra, the three bottom spectra, which were taken with the Gecko spectrograph around the 40, 50 angstrom region. And all of these features turned up. And simultaneously in Basel, one of John's postdocs was busily generating the expected spectrum. And as you see, that's the thing in the so-called lab up above there. And the agreement was dramatic and for us very exciting. So this encouraged us to start looking at other long chains, which we did over here in Victoria. And one of these was C3H2 or H2C3, depending on how you define it, which was known from radio observations. And when they took spectra of that in the lab, the spectra are these red dotted lines in these individual spectra. You've got an extraordinary coincidence between diffuse bands, particularly that one at 5450, a broad band. These were lifetime effects that were giving the breadth to the line, and also the one 4883. And the agreement seemed almost too good to be true. These were done both with the Plaskett and McCullough telescopes, but in order to be sure, we had to see certain triplet lines which were in the red. And in this case, we could not see them. It was not just a quality of our spectra, although in my case, I thought we could see traces there, but they were far too weak. And this essentially led to the idea being turned down. I'm still not clear in my own mind that we weren't onto something here, but I haven't convinced my co-conspirators on that one, particularly since there appeared to be no H2C3 in the direction of, picked up as radio signals in the direction of these particular stars. So what you see in this picture are a blue stellar spectrum, a rapid rotator, Alpha Leo, and then below that, the spectra of individual high temperature O star or early B stars. And the lab spectrum is at the bottom. And what they produce from the lab is, I can't believe it's quite what we expected to see, but anyway. So moving on. I was also working with Adrian Webster. I have to point out there are many people in the world who were working on these things at this time. I'm just giving you my perspective on the work that I was involved with. But Adrian Webster at the observatory in Edinburgh had some rather brilliant ideas. He pointed out that the structure in some of the diffuse bands, if they're narrow enough, might show the presence of isotopes if the molecule was large enough that successive substitutions of C13 for C12 would essentially broaden the line. And we saw this for quite a large number of stars. We were able to get a very good agreement. And Adrian, also looked at the profiles of some of the narrowest of the diffuse interstellar bands and attempted to develop models using TOPS. And again, he claimed that these profiles showed strong evidence for high moments of inertia, comparable with that of a Fullerene, and our work on the isotopes also suggested very large molecules. none of this was particularly earth-shattering, because I think by this time people had recognized that we were dealing with large molecules. Now, one of the candidates which were touted for a long time, and San Kwok is in the audience, so he can talk at length about these things, but PAHs, polyaromatic hydrocarbons based on benzene rings, these were assumed to be giving the infrared bands, which one could see for a number of heavily reddened objects. But searches for the actual signature of various PAHs, such as Kerning, came up short. There was no evidence for them. So I have to add in parentheses that I believe, I'm not supposed to talk about it, but there has been a detection of such things at radio frequencies very recently. So moving to this key paper in a Science in 1988 by Harry Kroto, he pointed out that you could take a PAH, and instead of having a hexagon surrounded by 6 hexagons, if you put a pentagon in the middle and substituted that and surrounded that with 5 hexagons, then you got a rigid, stable structure, but with curvature, which could then grow naturally into a sphere. And there were a number of magic numbers associated with that, C60 being one of the forms that would be most naturally to appear. And as I note there, he got the Nobel Prize in 1996, together with 2 others, for this work. Now, these were called Fullerenes after Buckminster Fuller, who had recognized the rigidity and strength of such a structure where you had pentagons surrounded by 5 hexagons. And this was supposedly incorporated into the biosphere at Expo 67. This is the origin of calling these things Fullerenes. Now, basically, Fullerenes are everywhere. We get incomplete combustion and so on. Here's a good example. But whenever you have a fire, such as this one, that's also producing Fullerenes. Now, what I found very interesting about this one, apart from the fact that it would have been a horrific accident if it occurred during Expo 67, is that I don't see a single pentagon in there. And in the fine print, I later discovered that, in fact, this was not built on the principle of pentagons and hexagons, but in fact, it uses hexagons throughout. So the whole idea of calling things Fullerenes, I don't know, in this age of alternate facts, we'll just let it go at that. Now, Fullerenes have turned up in meteorites, and again, you see in this mass spectroscopy of the Allende meteorite, there's quite a peak corresponding to C60. Also, the group at Western, led by Jan Kami, has detected C60 and C70 in planetary nebulae, or in a planetary nebula, I should say. Here you see the spectrum in the infrared at the bottom, in the black, and a couple of models, the different temperatures for the C60. And that's quite a good agreement. Jan is very active in this area of looking for Fullerenes. Also, there was a detection of C60 and Reflection Nebula by Mike Werner and others. The Reflection Nebula, NGC 7023, which you see an image in the bottom right left, is it's supposedly a site, and they mapped it across there. I won't go into that here. And if you look on the right, you'll see the so-called detections. Now, it's not those massive peaks, but it's tiny little peaks associated just on the edges. I don't consider those terribly overwhelming as detections, but fair enough. Now, in that original article in '88, Harry Kroto pointed out that the Fullerenes might be the source of the diffused interstellar bands, because particularly C60 has a low ionization, first ionization potential, and is rapidly transformed into C60 plus. So it's quite a compact soccer ball, about 7 angstrom across. And Bernard Foing and Pascale Ehrenfreund picked up on this idea somewhat later and pointed out that if C60 plus was or is a source, then there should be a couple of strong diffuse interstellar bands close to 1 micron, or around 9600 angstrom. But the problem was that at that time, there were no good lab values for the absorption lines. The only lab data available was the absorption from C60 plus in a very cold neon matrix, which of course, being a solid, introduces line shifts of an unknown amount. So what you see there are the 2 bands which they had proposed. They're not sharp. And you see that blue thing there corresponds to a stellar line, a magnesium 2 line. So the whole question was, were they, were not, or was it just a strange coincidence? If so, somebody needed to set up a different experiment to get the proper wavelengths. So here's the team that did it under John Maier. And they did this successfully, largely, in my view, due to this postdoc, Ewen Campbell, another Scotsman, I may add. No wonder he did so well. But the man in the red shirt is Dietrich Gerlich, and he built the equipment which will work so well. And what they built was this contraption here. It's better than a contraption. And you don't have to try and follow everything. But down here in the bottom, on the halfway up the right-hand side, they pumped in C60 gas, that is just raw C60. And the electron bombardment in this area here introduced C60 plus. They contained that here and selected C60 plus for carbon-12 only, and moved it into this region here, where it was flooded with helium buffer gas, which was at a very low temperature, less than 10 degrees Kelvin. And in this area, they've fired a tunable laser through the gas. And that had the effect that if there was an absorption in the C60 plus, it would be sufficient to energize the C60 plus atom, or in this case, ion, I should say, and kick off the helium, because we were dealing here with helium-bound complexes. And so the C60 plus would be released, passed down here, and eventually detected. So the impact of the passing the laser light through was to give you what would look more like an emission spectrum, because the more that came through, the more the absorption had been in the first place. If you don't follow any of that, don't worry about it. So this is what they got out. Here's the spectrum. First of all, they got the two strong lines which had been predicted by Foing and Ehrenfreund. They saw three other lesser features, and then a whole host of very weak features at shorter wavelength. And they were able to establish that the breadth of the lines was caused by partly rotational broadening and the lifetime of the excited electronic state. I'm not putting any of the term values and stuff in here. That would take too much time and gets the whole thing a bit too complicated. So you note that these lines up at the top here are about an order of magnitude weaker than those down below here. So once they got that, and as soon as they got this result, John and I started talking about, well, could we look for these lines? And we availed ourselves of the director's discretionary time at CFHT. We got a couple of hours from Doug Simons, very kindly. And here is a spectrum of that star I've already shown you, which shows very strong interstellar lines, interstellar bands. This is the full spectrum with the ESPaDONs spectrograph. There are about 40 orders concatenated here. That's quite a lot of effort, and that's, again, I owe to David Bohlender for having got all that correct. But the big issue is that the C60 lands feet first in a very strong water vapor band, telluric water vapor. So freeing the spectrum from that is a major challenge. Here's the blue star that we compared it with. This shows a spectrum of this bright star, which is a rapid rotator. By using a rapid rotator, one obviates the problem of the lines in the spectrum when one takes a ratio at the later stage. Again, you can see the strong telluric water vapor lines, and oxygen and hydrogen and water vapor down here. So we were lucky that the sky temperature is about -38. We'd have liked to have had a lower sky temperature. It means that the precipitable water was still possibly a bit more than a millimeter, but it was a lot better than you can get at most other observatories. So here is the region of the spectrum of interest. You note it goes from 9300 to 9600 angstrom. And this is what the spectrum looked like before division by the standard. And so what you see up here is a comparatively well cleaned up spectrum, but where lines are saturated, that is water vapor lines are, well, more than an optical depth of 2, then the cancellation is not total. And so you get lots of spikes and so forth. But these can be ignored because we can, they are of different width and importance to the diffuse bands, which we're looking for. Here's the diffuse band at 95.7. So let's take the next slide. Here is that again. Now in this ratio, excess absorption in stellar line, the star 183143 shows up as a peak. So here's the 95.77 diffuse feature. And these red lines correspond to the other three lab features of C60 plus. But over and above that, we also find right away that there are lots of other diffuse bands in here. This is a stellar line seen in reverse. Possibly even a diffuse band here. So not only are these lines of C60 plus present, we have a whole lot of other diffuse bands. And the real shortcoming, and the only shortcoming perhaps of ESPaDONs, is the fact that part of this order falls off the edge of the detector. And so there's a gap where we'd like to see the other strong line. So we've never been able to make direct comment about that line or so-called detection because it's missing from the spectra. Now, when one wants to see whether the lines which we have detected or the bands we've detected are actually coincident or congruent in wavelength with those from the lab, we have to take account of the interstellar clouds between us and this star HD 183143. And in this case, you see that there are two clouds which are separated by nearly 20 kilometers per second. And the strongest one lies about 12 kilometers per second to the short wavelength side of the zero velocity, and the other one just a few to the positive side. So what do you take? How do you line up the bands which we've found in the reddened star with the lab lines? Well, on this first pass, here is what we managed to do. But you hear this dotted line here corresponds to the zero shift. That is the undisplaced interstellar potassium line. And so we found that if we use the stronger of the two cloud features, we got good alignment between the lab, that's the dashed blue lines, and the stellar profile. And here you see the same thing at 9366 with the presence of another diffuse band, unknown, in the wing of that line. We get the same thing here at 9349, but we can't say anything about the 9428 line because there is an emission feature in the spectrum of the star. Well, this looked good, but we were a little worried, or I was worried, by the fact that we'd had to use just a single interstellar line to get the whole thing lined up. And so GRACES had come online, that is the fiber optic link between Gemini North and ESPaDONs in the CFHT dome. And it's a quite remarkable instrument because the fiber transmission is so exceptionally good. So again, we tried for some fast turnaround time in that same year. And again, we were lucky. We got just over 2 hours with GRACES. And here we looked at a different star, which has a very strong 4430. You see it here. Actually, I found that way back at the time of my thesis. This was just very strong. But you can see that in terms of this is the ratio you're looking at, by the way, this to a blue star. You can see that the compensation for the water vapor bands down in the infrared has been very good. And in fact, the water vapor was less than a millimeter. We were very lucky. It was a very dry conditions, and it turned out it was important because the the bands were very weak, or much weaker in this star than in HD 183143, which is a sign that the 4430 band is not part of a family with the C60 plus. Anyway, reverting to this question of the interstellar velocity of the cloud, here we see not necessarily a single cloud, but an unresolved component. It's not as sharp as it might have been if it was a single cloud, but it's still unresolved. And so now, because this was an earlier type star, which had fewer complications in the stellar spectrum, we made the comparison with the lab using this interstellar K line. And here you see the agreement or lack of it with 9577, 9428, which still has a small amount of emission in the wing, and 9366 with the new diffuse interstellar band, the unknown one in the wing here. And also the 9349 line, and the agreement which we had got with 183143 is shown here. Can I go back? Yes. So I was somewhat disturbed by this because it seemed to me that we were getting a consistent offset for HD 46711 relative to the lab values. So I had an exchange with John, and I said, I didn't exactly say there's something wrong with your results. He said there was nothing wrong with them anyway. But I said, have you taken account of the fact that that you were measuring the absorption of C60 plus HE, that is with HE stuck to the surface? And indeed they hadn't. What happened then is that Ewen went back and repeated the experiment for a series, selecting a series of different components or ions associated with different numbers of helium atoms. And so N, the number of helium atoms, is plotted along the bottom here. And the actual wavelength for these two important lines are here in the red on the right for the 9635, which doesn't appear in our spectra, but I'll come back to that. And 9577 over on the left here. And as you can see, that as one increases the number of helium atoms attached to the surface of the C60 plus, so the wavelengths increase. And extrapolating to a value of n equals 0 now returns to values which do coincide with the astronomical ones. So not only that, there was a re-observation of the C60 plus, which gave much better values for the relative intensities of the diffuse features. So returning to this question of what was appropriate for the star 183143, instead of saying, oh, it's this brighter component, whoops, I wish it wouldn't do that. Instead of saying it was this brighter one, now let's put in the true profile associated with two components here. And that's what we have in this upper here. We now have the correct wavelengths, that is the helium number 0. And for HD 183143, we have both components in the same relative amounts. And blue is the total. And as you can see, the agreement, for instance, at 9577 is now excellent. We also had time to measure one more star with graces, and that's included here. And we were able to get much better profiles of the 9428. This is the star number here, 169454. And as you can see, we were getting now appropriate agreement between lab and stellar observations. Here are some of the other lines where we have the presence of the, these green ones now are the unknown diffuse bands which we found in these regions. But the agreement with, and as you can possibly also notice, these green bands do not vary in unison with the red bands. That is, whatever they are, they're not of the same family and very unlikely to be associated with C60 plus. So this looked pretty good. Our earlier work had been subject to a lot of harsh criticism because we didn't get proper agreements and this, that, and the next thing. But this blew most of that away. And finally, we went back to the data from Foing and Ehrenfreund and re-reduced it for the 9632 feature, which is, everybody knew, was being affected by a stellar line in the profile, for which we had to make correction. So we had an observation for Rigel, which is almost similar, very similar to HD 183143. And we took that profile and removed it from the so-called C60 plus profile. And this, if you like, goes all the way back now to the work of Foing and Ehrenfreund. And we have used both components here. And when we did that, we get excellent agreement. And this, of course, is the other magnesium-2 feature, which we talked about before. Now, at the same time, Jan Kami and his colleagues used HST, the STIS spectrograph, which was much lower resolution than we had, but enjoys the fact that it's well above the Earth's atmosphere. And they looked for these C60 plus features there. And basically, although it's much coarser resolution, and they were looking at different stars, which is good, they saw all of the same things which we had seen, including, of course, these additional diffuse bands. So if we look at 9348, the red is the predicted profile from the lab, and within their areas of observation, it all looks pretty good. They also didn't look at the 9632. I think they were somewhat bold in saying that they had now finally proven it, since our stuff was questionable, but that's science for you. So what has happened, this was basically stepped you through a bit of research and how one got to a convincing conclusion that certainly starting with the way back with Harry's work, and the Foing and Ehrenfreund, we have reached the point where we can say that C60 plus is definitely a source of 5 diffuse interstellar bands. We don't know if it's if there are any other, but there do not appear to be any others that we could detect in the stellar spectrum. This is very much a work in progress. John Maier has now retired, And Ewen Campbell has moved to Edinburgh and taken all the equipment with him. And he's drumming his fingers at the moment because he can't get into his lab. And he has already got some rather interesting results. One thing we did look for was the C70 plus, but unfortunately it has no strong origin bands. And again, these lines, which were all determined by the same technique as for C60 plus in the lab, land in the middle of atmospheric oxygen lines. So they're difficult to disentangle if they're there, but we would have not been able to see them. This is a meeting of us all in Edinburgh 2017 to discuss the future. I wouldn't have put this in, but for those of us who are retired and wondering whether we should keep going, I just wanted to highlight Sidney Leach, who gave one of the more important and lengthier papers. The day after this photograph was taken, he celebrated his 90th birthday. There we are.
Thanks, Gordon.